Yeah, well, it's a great pleasure to have with us tonight Antonella Santo, who's Professor of Particle Physics at Sussex University and Royal Society Merit Award holder, who's going to tell us about, this marvellous bit of equipment that sits over there in Switzerland and tells us about what's it all made up of, basically. So
a nutty bit of kit.
yeah, it's a very nice bit of kit. So over to you, Antonella, I think, and we'll do the usual and have the questions and answers at the end. So that's good.
Thank you very much. Thank you very much for the invite, and thank you all for being here this evening. The title of my talk, The Big Bang Experiment, hopefully will become a bit clearer soon enough during the course of my presentation. I work on the Large Hadron Collider, and so this is the science I will be covering tonight. But without further ado, let me get started on this journey. And a good journey starts always with good preparations, and often enough we need a map. And we particle physicists, scientists in general, but particle physicists often like to think about themselves as of explorers, pushing the boundaries of knowledge. And in the Middle Ages, during the golden age and the modern era of the golden age of exploration, that was very much the same sentiment that drove people to go off and explore. And in the Middle Ages, at the time of Ptolemy, that you see here on the left, cartographers used wild beasts, dragons, sea monsters to mark uncharted territories. And Ptolemy, although he's perhaps better known for having been the one who formalized the geocentric model of the universe, had many talents. He lived in the 3rd century AD and was one of the great intellectuals of his time. He studied mathematics, astronomy, and also geography. In his geography treatise, he compiled all the geographical coordinates of all known parts of the world, which he called the ecumeny. And in this manual, pretty much was an instruction manual on how to construct maps. And the maps that were constructed based on Ptolemy's geography treatise were not the most accurate. Here at the bottom right, you can see what would have been the map of Britain obtained from Ptolemy's instructions. And you can vaguely recognize the kind of usual images of the British Isles, but it's a bit of a far cry from the very accurate images that satellites and, for example, NASA releases lots of those on a regular basis. And we're also nowadays used to seeing images of our planet from the ISS. So it's a different pair of shoes, but nevertheless, that was the best that was available in those times. While explorers, these precursors of modern scientists, began to collect more reliable data, so the people who produce maps started to organize the whole lot of information into more accurate maps. And what you see here is the map that was commissioned of lay brother Fra Mauro around 1450 by the Signoria of Venice, where he was asked indeed to produce the best map of the world as it was known today. And we're talking about Renaissance times, so a lot of creativity. And Fra Mauro departed from the convention of putting Jerusalem as the middle point of any map. He didn't do that. And also he decided to display the world upside down. So what we see here at the top is what we see normally as the south part of our the southern hemisphere. And at the top we see, at the bottom we see the northern hemisphere. And around here, off the coast of modern day Senegal, Framauro also placed an island called the Isle of Dragons, because dragons were like the symbol of unexplored territories, territories where dangerous beasts were thought to perhaps inhabit that region. But very much that was a way to say, beyond this point, we don't know what's there, and more exploration is needed. NASA has not so long ago released computer-generated images of our planet from a collection of satellite images that depict the world with the same orientation as Framauro's map. And you can see that actually it's very, very similar to Framauro's Mappamundi. So even though we're talking about something that was produced in the 1450s, that, I mean, was something that enabled Framauro, for example, to first kind of gather the perception that the world was a sphere, and also, like any kind of well-educated person of his time, but also he was able to estimate the radius of the Earth within about 10% of its actual value. So quite remarkable if you think of what kind of instruments were available in those times. And instruments really are what any good explorer needs to orient themselves and proceed with the exploration and make sense of what the exploration brings along. So in ancient times, the most precise instruments would have been astrolabes and other navigation tools. In modern times, our instruments, if we want to push the boundaries of knowledge in fundamental physics, we use instruments such as very powerful telescopes to look at the universe, but also very powerful particle accelerators that, as we will see, enable us to look at matter and its constituents at its very fundamental level, and also has a connection that goes from the very small of the microscopic world to the very large scales of the universe. We also produce maps with data that we collect, we physicists and astrophysicists and scientists in general. We have to organize our information, our knowledge into an organized system. And here what you can see is pretty much a map made by astronomers in this case, obtained by putting together data collected by the NASA Hubble Space Telescope. Just to explain what I'm showing, tinted in blue, we see the distribution of dark matter in the center of the Able 1689 cluster. Able 1689 is about 2.2 billion light years from us. And Hubble couldn't see dark matter directly. Astronomers infer the presence of dark matter by analyzing the effect of so-called gravitational lensing, whereby the presence of dark matter distorts the pathway of light before it reaches us. The dark matter in between us and the cluster gets deflected, and from those deflections it is possible to kind of reverse engineer the observations and extract information about the spatial distribution of dark matter. And I'm already kind of mentioning this concept of dark matter. I will come back to this more than once over the course of my presentation. Still sticking with this parallel of maps, and I know that some of you in the audience have been involved in the early days of kind of studying the cosmic microwave background. What we see here is another map in which variations of the cosmic microwave background is displayed. For those of you who are maybe not so familiar with the cosmic microwave background, it is a low energy radiation that fills our universe completely. And the map that we see here, again, is constructed from putting together astronomical observations, but also by using the theoretical models necessary to interpret those observations. The patterns of this map, the blue and the red and the yellows, they can be seen as kind of temperature maps. So the cooler colors correspond to downwards fluctuations on some level of, let's call it temperature, of the cosmic microwave background, and the hotter colors, the yellow and the red, are upwards fluctuations over that baseline. And these fluctuations, upwards and downwards fluctuations, the fact that it's not uniform, the temperature is not the same everywhere, we don't see just one single color uniformly kind of distributed over the map of the universe. The same fact that we see these kind of anisotropies, these kind of variations of a space, have to do with how the early universe developed, but also are affected, those fluctuations, by the presence of dark matter in the universe. This dark matter, which is invisible to the eye, invisible to any telescope at any wavelength, of which we infer the presence from other indirect observations, such as the rotational curves of galaxies. And so from maps like this, we extract information about the deepest mysteries about the universe. And another kind of map that I'm also showing on this slide is a representation of what is known as the standard model of particle physicists. Particle physics explore, while cosmology looks at the sky, looks at the universe on a very large scale, and kind of even projects images that look at the small variations of temperature on scales as large as those of our universe. The standard model of particle physics presents an organized description, hence a map again, of the world of subatomic and subnuclear particles and how they interact with one another. And I'll come back to the standard model and what these various symbols mean. But you can think of it as some sort of turbo version of the Mendeleev table. You know, the table that organizes chemical elements. In this case, we are organizing elementary particles, both the ones that interact with one another and the ones that enable those interactions. And the last particle of the standard model to be discovered was the Higgs boson in 2012. And in fact, yesterday, it was already the 9th anniversary of the announcement by the ATLAS and CMS collaboration of the discovery of the Higgs boson. So this talk tonight is a kind of nearly on the so-called birthday of the Higgs boson. But why did I give my talk the title, The Big Bang Experiment? And let's think about the Big Bang a little bit. From analysis of various maps of our universe, such as the ones that I've indicated and discussed briefly previously, cosmologists, those physicists who study the fundamental behavior and origin of our universe, they have arrived at what we now consider the prevailing cosmological model of the universe, the Big Bang theory. And the Big Bang theory describes how the universe evolved from a very early high density, high temperature state to the much less dense and much cooler universe that we see and live in today. Since the Big Bang, the universe has been expanding and cooling down. From measurements of its expansion rate, we know that the age of the universe is today of approximately 13.7 billion years. The Large Hadron Collider smashes particles together at some energy, and that energy that we reach at the Large Hadron Collider can be made to correspond to a specific age of the universe. How is that so? Remember that the universe was very dense, very hot object early on, and that through its expansion, it's been cooling down. So the kind of energy density has decreased. That means that in correspondence to a time arrow that goes from the early instance of the existence of the universe, where forces appear, then elementary particles appear, then later on the universe is cooling down to the point that quarks can be kind of they collapse together and form nucleons, protons and neutrons, and then those later on form nuclei, and nuclei with electrons form atoms, and from those gases forms nebulae and galaxies, planets, and so on, up to reaching the current time. All of this happens over time while the universe is cooling down. So if we reverse this movie from the temperatures that we see today, the temperature of the cosmic microwave background is of 2.7 Kelvin, which is nearly 300 centigrade degrees below zero. If we reverse this movie and try to go from the present time towards the early kind of development of the universe, we will find that the energy was higher, the energy density was higher, and so the temperature was higher. So we can reach the point where the energy in the universe would have been approximately the same as the energy that we can reach at the Large Hadron Collider. So we can then look at the correspondence between the temperature energy arrow and look at what that corresponds to in terms of time. And we find that the energies that we reach in the Large Hadron Collider correspond to approximately an age of the universe of about 1/10 of a billionth of a second after the Big Bang. So by studying the interactions between elementary particles at the energies that we can reach at the Large Hadron Collider, we are pretty much recreating in the lab the conditions that would have existed in our universe only 1/10 of a billionth of a second after the Big Bang. And in that respect, we can think of the Large Hadron Collider as some sort of time machine that enables us to explore the physics of the universe in those early times. So when we look at the world, we're not aware of the discreteness of its makeup, but particle physics has transformed the way in which we look at the universe. By looking at those incredibly small distances that we can explore with the instrumentation typical of a particle physics experiment, we can explore how matter and forces work, and we get to understand the world around us at its most fundamental level. by colliding particles at very high energies and by looking at them through our super microscopes. I will show you pictures of these microscope in inverted quotes, the kind of detectors that we use in collider experiments. But by inspecting data and kind of enabling ourselves to inspect the interactions of matter on very short scales, we discovered that actually matter is not kind of one continuum, but it's made of atoms, and atoms themselves are made of nucleons and electrons, and this is probably not surprising anyone. But then when we go to smaller scales, we find that the nucleons are the nuclei are made of nucleons, so protons and neutrons. But then at even smaller scales, we find that the protons and the neutrons are not elementary particles themselves, but they are made of quarks glued together by other particles that we call gluons. So it's a little bit like having Russian dolls that you open one and you get a smaller one, and there's a different story maybe painted on that smaller one, and then you keep opening and opening until you reach the point where, at least as far as you can see, there isn't anything within it, and you have reached the truly kind of core of that set of Russian dolls. And as far as we can see, quarks and gluons and electrons and other particles that resemble the electrons truly are the elementary particles that we need to understand. And so here I have again that map of the standard model, and I want to explain a little bit more what this wheel represents. So on the outermost part of this set of concentric wheel, we see two sets of particles. All of them together are known as the fermions. This has to do with how these particles interact in the presence of a magnetic field, in the presence of a magnet, let's say. And the top half are the so-called quarks, and there are 6 of them: the up quark, the down quark, the charm, and the strange, and the top and the bottom. I don't kind of read them off one after the other because they come together in pairs. And parallel to those, there are another setups now. Again, they are fermions. They have the same behavior in the presence of a magnetic field as the quarks, but they have different kind of properties and different kind of interactions with one another and with other kind of particles. And the electron, one of the basic constituents of atoms, is in fact a lepton. And then there are other 2 charged leptons, heavier than the electron, but similar in kind of many of its properties: the muon lepton and the tau lepton. And then to go with them, there are 3 neutral, electrically neutral, they do not carry any electric charge, neutrinos, which carry a memory of the charged lepton that they are paired with. So for the electron, we have the electron neutrino, the muon, we have the muon neutrino, and with the tau, we have the tau neutrinos. And then the second wheel around this is that of the forced particles. And finally, we have the Higgs boson. And now I want to tell you a little bit about these particles, one at a time, well, one group at a time. But the one thing that I want to remark first is how everything around us, really, you and I, and the things that make anything that you observe, what we call ordinary matter, the matter that would shine through a telescope if you looked at the sky, but also the matter of your body and the table and the chair you're sitting on, the air that we breathe. This is all made by pretty much 3 fundamental fermions: the up and the down quark. These are in some combinations glued together to form the protons and the neutrons in the atoms, in the nuclei inside the atoms, and then the electrons that kind of orbit around the nuclei. These are the three main constituents of ordinary matter. The other particles that we see, the heavier quarks, the heavier charged leptons, and the neutrinos, they can be produced. They are produced not just in accelerators, but also cosmic rays and from the sun, lots of neutrinos from the antineutrinos from the sun, and nuclear reactors, and so on. But you wouldn't normally expect to find them in ordinary matter. And they interact with one another, these fermion particles. These are the matter particles, the fermions. They interact with one another through the exchange of the so-called forced particles. These would be what we call the gauge bosons, which transmit the forces of nature. Now, we know that there are four forces of nature: the electric force, the electromagnetic force, electric and magnetic force, which is responsible, for example, for keeping your computer running and allowing us to have this lovely meeting this evening. We have the gluon, which transmit, and this is, I mean, the electromagnetic force is transmitted by the photon. Then we have the strong force, which is responsible for the nuclear force, which is what makes the table or the chair that you're sitting on solid. And so the gluon is the particle that is responsible for transmitting the nuclear force. And finally, we have the weak force, which is transmitted by two kinds of particles. The W's, there are two of them, one with a plus, another one with a minus charge, and the Z bosons. And the weak force is, for example, responsible for radioactivity or for the nuclear kind of processes that keep the sun shining. Noticeably absent from the standard model is gravity. Maybe the force that we are mostly aware of is not described by the standard model, which by itself is one big missing block in the standard model. And then we have the Higgs boson, and I will come back to that. This, as I said, was the last building block of the standard model that was missing and was finally discovered in 2012. Now, when we look at the particles in the standard model, we notice one thing, which is that the masses, the kind of the substance of these particles, is not the same for all the particles. Some of the particles, the up quark, down quark, and the strange quark, and then all of the leptons except for the tau lepton, they're all very, very light. Their masses are non-zero, but nearly negligibly small. Some of the particles in the standard model, the photon and the gluon, have got a mass that is exactly equal to zero. The photon, which is the light particle, has a mass which is exactly equal to zero, and the gluon, which is the particle that transmits the strong force between the quarks, is itself exactly massless. On the other hand, around this wheel, there are rather more massive particles. The tau lepton amongst the leptons, and the charm and the bottom quark, they all are in the range of a few units of the proton mass. So we go from very, very small, nearly negligibly small, to exactly massless, and now we have something which is a few units of, we have some particles which are a few units as massive as the proton. Some of the particles in the standard model are a lot more massive than that. The top quark, the W and the Z bosons, they have masses which are of the order of between 1 and 200 or thereabouts units of the proton mass. So why on earth do these particles have this pattern of masses? In fact, why do they have a mass which is non-zero at all? Why do they not all have a zero mass? And this takes me to talking about the Higgs mechanism and the Higgs boson. So the Higgs mechanism explains why elementary particles do carry a mass which is in most cases different from zero. And you should imagine that there is what we call a Higgs field, some sort of, well, think about some sort of molasses that fills the universe and that interacts with particles in different ways. So if we didn't have this molasses in the universe, all the particles, the photon, the electron, for example, even the top quark, which is the most massive of the elementary particles, without the Higgs field in the universe, they would all have exactly the same mass. They would all have a mass which would be identical to zero. That means that they will all travel. I mean, I hope you can see that the bigger the inertia of an object, the slower it will be if they are subject to the same force. So if all the particles were massless, they would all be traveling at the same speed, and that would be the speed of light. This would be the situation with the field off, with no Higgs field in the universe. Now imagine switching on this Higgs field. The universe is now filled with this molasses that interacts differently with different particles. The photon will not be disturbed in its motion by the presence of the Higgs field. So it was traveling at the speed of light before it continues to travel at the speed of light, by definition. But then the electron would have some interactions with the molasses, and so the electron particle gets slowed down while traveling through the Higgs field, and that corresponds to assigning a mass to the electron, which is small but non-zero. So it is slowed down by going through the Higgs field. The more massive particle, the top quark, is the one which has the greatest interaction with the Higgs field. Because it interacts a lot with the Higgs field, it is slowed down more than, for example, the electron. And because of that slowing down, you can see that that would correspond to the particle having a larger mass. Now, this is all quite naive, but I hope it gives you a sense of how the presence of a Higgs field that interacts with particles will essentially correspond to particles acquiring a mass which will be smaller or larger depending on whether the interactions of the particle itself with that field are less or more intense. The Higgs field is not the Higgs boson. The Higgs boson is kind of clumps of that field, if you wish. So when we discovered the Higgs boson in 2012 and completed the standard model wheel with this last missing block, we didn't find the particle that itself is responsible for giving particles a mass, which is kind of the statement that we hear often enough. But it's a particle that, through its existence, proves the existence of the Higgs field. And it is the Higgs field that is responsible for the mechanism that gives particles their mass. So where did we discover the Higgs boson? And I've already mentioned Large Hadron Collider multiple times, so I now want to give you an overview of where it is and what the detectors that operate at the Large Hadron Collider, such as the Atlas detector, which is the one in which I am involved, what do they look like and how they detect particles. So first of all, let's locate the Large Hadron Collider geographically. It is across the border, the French-Swiss border near Geneva. Here you can see Lake Geneva in the background. At the very top here, you see a section of the Alps. On a clear day, you can see Mont Blanc from CERN. And the perimeter of the Large Hadron Collider, which is located about 100 meters underground on an inclined plane, about 100 meters underground. The length of the perimeter is 27 kilometers. And we collide proton-proton beams at unprecedented high energies. And the Atlas experiment is in one of the caverns. This one would be just across the road from the CERN main entrance. Just to give you an idea of what 27 kilometers underground means, what kind of engineering feat that means. Here I've drawn a circle of the same size, but centered it on Headingley. I found this little app that allowed me to do that. So I don't know the geography of your part of the world very well. I've been to Leeds, but this looks like something that maybe will impress you more than it does me, because maybe you have a sense of how long it takes to drive from one village to the other. And that will give you a sense of how long it takes, for example, to drive along the French-Swiss countryside to go from one experimental location to the other. And the energies that we reach, we measure them in these funny units that particle physicists use, tera electron volts. 1 electron volt is the energy that 1 electron takes to go through a gap that is kind of at a potential difference of 1 volt. And these high energies correspond in terms, if you were able to release all the energy that is contained in such collision of two small kind of cruise ships that are moving at about 30 kilometers per hour, if you're able to extract all the energy from that collision, that would be the energy that is contained in a proton-proton collision at the Large Hadron Collider. Protons in the two beams, the counter circulating beams that are made to interact at very specific point, they travel nearly at the speed of light, only 1 part in 100 million smaller than the speed of light. They go around the circle about 11,000 times per second. And the pencil thin beams are made to smash head-on at precise location. And as a comparison, you would have to be able to smash two embroidery needles which are fired from 10 kilometers away to reach the same comparable precision that is needed to make the two proton beams smash head-on against one another. And the temperature reached in magnets, which are needed to keep the particles around a circular orbit at the Large Hadron Collider, they are only marginally less cold than the coldest place in the universe, which is the Boomerang Nebula, of which you see a photo here to the right. So the Large Hadron Collider is certainly the coldest place on Earth, and in fact, one of the coldest places in the universe. And when we collide particles together, thanks to the famous identity made famous by, discovered by Einstein, E equal mc squared, we know that if there is a certain amount of energy, it is possible to create particles of a certain mass, where the connection between energy and mass is given by this identity, where c squared is the square of the speed of light. So a certain amount of energy corresponds to a maximum amount of mass that one can produce. And it also tells us that the two protons won't necessarily remain protons, right? Other things can be created in the final state from the proton-proton collision, as long as the E equal mc squared identity is preserved. So we can start off with here in this picture, just to kind of give a pictorial example. You start off with two apples, the two protons, and you might end up with oranges and pineapples and lots of other things, while total energy is conserved. In fact, you might have produced in this proton-proton interaction a Higgs boson, and then this Higgs boson would have to manifest itself in some ways in your detector for you to discover it, or for you to observe it now that it has been discovered already. But some other times, other particles, which are not part of the standard model, might have been created. Some new particles from an extended version of the standard model, which, as I said, is known to be incomplete, if nothing else because gravity is not described, but there are other reasons why we consider the standard model to be incomplete. So some of these new particles, which might have been predicted by certain theoretical extensions of the standard model might have also been produced in our data. And we want to figure out whether that's the case. And how do we do that? First, we need to understand what those collisions really are, because I've been mentioning apples and bananas and oranges, but the world is a lot more complicated than that. So if you have protons that collide with one another, remember that the proton isn't an elementary particle in itself. It contains quarks and it contains gluons that glue together the quarks in the proton. So really the hard, what we call the hard interaction, the high energy interaction that happens, which sometimes will produce interesting new particles in the final state, will not be just a simple scattering between two high energy bolts. I mean, there's a lot messier kind of environment where lots of other particles are produced. Those particles may emit more particles, which may split into more particles, and then these might decay into further particles and so on, up until the point you can imagine that in this interaction, this red ellipse represents the interaction, kind of moving outwards, you are essentially following what happens in this event, very, very rapidly happens in this event, until we get to the point where we got all the objects which are observable in our detectors. So all of the red lines and yellow line and the light green blobs, there will be some sort of intermediate stages of the interaction, but the little green dots and the wavy lines that we see in the outermost layer, they will be the actual particles observed in the detector. And how do we see all those interactions? We see that through the eyes of detectors such as the Atlas detector. This is a picture of the Atlas detector seen from the side. The blue cylinder here is where the one of two proton beams would be coming from. This is while the detector was being constructed. Normally it would be kind of close together like one big cylindrical plug, and there would be another beam coming from the other side. Now this is the Atlas detector. Again, while it was being constructed, the scale, just look at the size of this gentleman here. And this is the innermost plug, which is being inserted, the inner detector. And we're looking at these images if we were riding on top of one of the beams. So the beam would be entering the screen right now. The Atlas detector is a very large object. For those of you who are familiar with the Brighton Pavilion, I've got here an image, kind of the comparison, is nearly 6-story building, as high, as tall as the Brighton Pavilion, and twice as long. Very heavy, same amount of, kind of the same weight as the Eiffel Tower. That also tells you the level of engineering that is required to install such a detector 100 meters underground, and to do that really, really precisely. And we use the Atlas detector as some sort of very powerful microscope that enables us to inspect nature at its most fundamental scales, 10 to the minus 13. So that would be 10,000, 1 over 10,000 billions of a millimeter. And to do that, we kind of have to, like good sleuth, we have to look at the data that we collect with our experimental setup, and the data gets run through computer-based algorithms that give us pixelated images with various degrees of precision that kind of we need to use to infer the presence maybe of a Mona Lisa in our data. And we need to look at all these images and decide whether or not to collect them. Now, the detector itself doesn't give you images like the one that I'm showing. These are obtained after rather complex analysis of the data, and we represent all the various particles with specific kind of geometrical representation. Here we see the longitudinal image, the one kind of riding the beam at an angle. This point from which all the various yellow lines depart is the interaction point. All the particles are produced. The yellow lines are the trajectories of the electrically charged particles. The various green rectangles and yellow rectangles will be energy deposits in various layers of the detector that measure, for example, the energy of photons, the energy of other particles known as hadrons, and also try and identify the nature of the particles. And so from all that messy environment, we need to figure out, for example, if the Higgs boson was produced in that interaction. And as much as we can think of the Atlas detector as of some sort of in function, a very sophisticated microscope, we can also kind of understand it as a very powerful, fast digital camera. The Atlas detector has got about 100 million digital channels that will correspond to 100 megapixels. Your camera would have to be that level of precision. And because of how fast these beams go around the Large Hadron Collider, how often they collide with one another, there are 40 million particle collisions per second. So that means you can think of the Atlas detector as of a digital camera that is able to take 40 million snaps per second, and each one of those images would contain 100 megapixels. So that's a lot of data. It's a lot of data to collect, it's a lot of data to analyze. And in all that data, we want to find the Higgs boson, for example, or maybe find these yet to be discovered exotic particles. So it's a proverbial needle in a haystack. Can we collect all the data and then analyze it later on? In actual fact, no, we can't. There's too much data. We wouldn't have enough capacity to store it all, and we wouldn't have enough computing power to analyze it all. So we have to make a decision as to which data we keep on permanent storage for later analysis. And we do that based on features that the data has, interesting features. Remember those images where you have to figure out whether you got the Mona Lisa in your data or not. We have what we call the trigger system, which is some sort of brain of the experiment that takes those 40 million snaps per second, sieves it, and in various stages, some of which are hardware-based, some of which are software-based, decides whether or not that particular proton-proton collision might have contained some interesting physics that deserved being kept on permanent storage for later analysis. And we save all those 40 million snaps per second. We end up saving order of 100 to 200 of those. Now, to imagine, again, give you kind of an intuition of how difficult that would be the same as having 25 kilograms of sugar and being able to look at all the grains one by one in those 25 kilograms of sugar to find about 200 grains of salt, sorry, 200 grains of, maybe you got white sugar and you want to find 200 grains of brown sugar. Those are the ones that you keep. And maybe amongst those, there will be one that might be Higgs boson. Maybe there's a grain of salt. So in 1 second, you need to sieve 25 kilograms of white sugar to find 200 grains of brown sugar. That's the kind of fast detectors that we need to operate. The amount of data is also very, very large, even though we essentially, I don't want to say throw away because we know what we're doing, so it's not like we lose information, but we do not keep for permanent storage all of the data that is produced, only a small fraction of it. Nevertheless, the amount of data that the Atlas experiment collects every year while it's running is pretty much comparable to the Facebook uploads or to Google search register in a year. So very respectable amount of data. That's why we talk about big data a lot when we talk about analyzing Large Hadron Collider, data from Large Hadron Collider experiments. I need to speed up a little bit. I realize we're going, yeah, I've been going for a while. So let me now kind of move away from the details of the Atlas experiment and the Large Hadron Collider and go back to maps for a second. And this is the Spilbury jigsaw. I really like this image because the Spilbury jigsaw, first of all, was the first purpose-made jigsaw in history, apparently. And there are some missing pieces being retrieved, but there are a few missing pieces. And it reminds me of the Standard Model, because the Standard Model is quite beautiful, like the Spilbury jigsaw. It's a map. It enables us pretty much to look at the landscape and guess what we're looking at, but there are holes. We know that there are holes, that there are missing bits of information. We haven't got the full picture of the world. If we only looked at the Spilbury jigsaw, we wouldn't know about very important parts of Europe. And so we know from the Standard Model that there are missing bits, not just the fact that gravity is not described by the Standard Model, but there are phenomena, experimental phenomena that have been observed, neutrino oscillations. More recently, we're seeing cracks in the Standard Model coming from the study of the muon lepton. So we know that there is stuff that is not described by the Standard Model, that we need to go beyond the Standard Model. One big reason why we know we need to go beyond the Standard Model is from this analysis of the cosmological maps, which enable us to infer the existence, as I hinted at the start of my talk, of dark matter. Of the matter that makes our universe, only a small fraction is made of ordinary matter. Remember the up and the down quark and the electrons. But even the heavier quarks, all the particles that are described by the Standard Model, they only make up a very small fraction of the matter in our universe. The large part of matter in the universe doesn't shine through a telescope. Only 5% does. The remaining part of the matter in our universe doesn't shine through a telescope. And that's why we dub it dark matter. We don't know what it is. We are trying to figure that out. There are experiments that search for direct evidence of dark matter. They hope to see dark matter particles coming from the sky and interacting with the particle detectors underground. In our case, we try to produce dark matter particles at the Large Hadron Collider if they are in the correct range of masses that can be produced at the energies of the Large Hadron Collider. The remaining part, I don't know, it's flipping back and forth, just let me go back a couple of slides. The remaining part of the universe, about 75% of it is what we call dark energy, which is some force that repels gravity, but the Large Hadron Collider doesn't attempt to give an answer for that. But then I made the parallel between the Large Hadron Collider and the Atlas experiment as being a powerful microscope or being a powerful digital camera. And so now we see how the Large Hadron Collider can also be seen as some sort of powerful telescope. We're not really looking at the sky, but we are exploring physics, which is very important for understand how the universe works. So in a very broad term, we can think of it as some sort of additional telescope that enables us to study the cosmos. And what could there be beyond the Standard Model? There are many hypotheses. Some hypotheses postulate the existence of heavier particles that kind of mirror image the Standard Model particles, and they would have properties maybe similar to the ones of the Standard Model particles, but because they are so heavy, there hasn't been an experiment that has been able to produce them yet in a lab. And so the hope would be to see some of these mirror images of Standard Model particles, some of which might in fact explain the nature of dark matter. Some of the particles that we might be producing, if nature allows us to see them at the Large Hadron Collider, they might be in fact dark matter particles, and we search for them in the Atlas experiment and in the Atlas experiment's kind of friendly enemy, which is called CMS. So we might, in fact, one day give an answer to at least one of these large outstanding questions about the nature of the universe if we were fortunate enough to produce dark matter particles in our detector. But that's only one of the things that we can search for. We're not too picky. If we found anything beyond the standard model, we would be happy, whether or not it's dark matter. But that's one big motivator to search for dark matter, to search for beyond the standard model physics at the Large Hadron Collider. And I'm drawing to a close very soon, but I want you to ponder how what we do really proceeds along two routes. One of them is the experimental route, and the other one is the theoretical route. So all these postulated theories that expand the standard model and go beyond the standard model are developed by our theoretical friends. And we as experimentalists are given the job of either demonstrating the validity of those theories or maybe disproving them. So what we do all the time to try and fill the gaps in the Spilsbury jigsaw, which is the standard model, we compare theory and experiment. And we want to figure out whether a theory is correct or not. And sometimes you discover something new, but sometimes you add to the knowledge of the world by just, well, not just, but by kind of making a statement on whether or not a certain theory is valid or maybe needs modifications. So that's how really progress is made in fundamental science. Now, imagine that we are comparing the red line and the black line, both of them being lines that predicted by some theories, two different theories. We need to compare them to experiments. And imagine that those, the size of those lines corresponds to how precisely we are measuring a certain quantity that we are comparing data to theory. And so imagine that we need to compare those two theoretical lines to the experimental line in a region where actually, if the precision that we have is the one that we are displaying, it's very difficult to make a statement that is informative, because in reality, within the thickness of those three lines, both theories are equally compatible with the experiment. So we can't say much if that's the level of precision that we reach. On the other hand, if we work really hard, both on the theoretical predictions and on experiments, and we manage to reduce the thickness of those lines by reducing our experimental uncertainties, but also reducing the uncertainties on theoretical calculations, we might end up being able, in this case, to exclude, to prove that the theory represented by the black line is not valid, while the theory represented by the red line may be valid. Maybe we are not able to state completely that, yes, that's it, because maybe there are other theories which are compatible with our experiments. But what we do by searching for new things and maybe not finding them is not a waste of time, right? We are able to say, actually, theory one is not that interesting anymore because my experiment is now proving that it doesn't agree with it within uncertainties. So we might be able to locate some places on the Spilsbury jigsaw, but we might still end up with some little gaps. And so still needing to figure out what is going to fill that gap, what is missing yet. But we might be able to throw away the very good but not legitimate copy of the Mona Lisa and kind of stick with the original. The Large Hadron Collider has been running for a few years. We've had one first shutdown. Now we are slowly ramping up in the second long shutdown to start to take data at a much higher beam intensity. And we're only beginning to scratch the surface. A lot has been done, but a lot has been said, and the Higgs boson discovery came quite early. after switching on the Large Hadron Collider. But there is a lot more that needs to be done. A lot of the rare processes that we want to study, they require a lot of data to be investigated fully. So the intensity, increasing the intensity of the beam will do a lot, and then there will be a second shutdown when we will refurbish not only the detectors but also the accelerators, so that we can collect a lot more data in a much shorter period of time, and so try and kind of follow those cracks and hopefully kind of uncover more mysteries of how particles interact at the fundamental level, and by doing so saying more things about the construction of our universe. So please stay tuned. As I said, I'll be coming online very soon. We expect beams again in 2022, and we already starting to think about kind of so-called commissioning shifts, and hopefully it will be possible also to travel back to CERN in person again soon. We have continued to work very hard throughout the pandemic. We are a very large global international collaboration. We were very much used already to working in front of the screen and collaborating with colleagues from Japan, from Canada, or the Southern Hemisphere. We have continued to do so throughout the pandemic, but it will be lovely when we can all go back to CERN and maybe find something new and exciting to share with you next time we can have a beer in person as well. So this is it for me. I will now stop sharing my slides. Thank you very much for your attention.
Thank you very much, Antonella. That was wonderful. Thank you. Extremely informative. Can I ask if anybody has got a question or a comment? Could you put that in the chat, and then we'll ask you to pose it. I guess there's quite a lot of information that you've put forward there. So it might take a little while to sink in for some people. Oh, here we've got something already from Kieran McInnery. Would you like to?
So the question is, the LHC recreates temperature conditions shortly after the Big Bang. Temperature is only one variable of a system. What other variables are relevant to represent the early universe? So indeed, I mean, temperature is a really good way to describe a thermodynamic system, which the universe really is. You can think of the universe in thermodynamic terms, and so being able to give a temperature for the universe is very important. But then, as you might remember from the slides that I was showing, the anisotropies, I mean, the variation of how the universe develops, and maybe parts of the universe might have been accelerated differently early on. They are very, very important indeed, and they would have had great significance to determine the universe that we see today. So yes, there are lots of more variables that one would have to think of, but if we describe the universe in thermodynamic terms, being able to give its temperature is important and general.
Thanks for the question, Kieran. I was wondering if you had that picture at the beginning where you were saying you could go closer and closer to the Big Bang, the start of the Big Bang. How close are you still trying to get closer than you are at the moment to a hotter universe? You
mean this image here, right?
Yeah.
So there is this kind of intrinsic limit, which is the 10⁻46, which is really, I mean, you shouldn't imagine that the Big Bang really was this big explosion. But I mean, there are theoretical limitations that kind of, it's impossible, even theoretically, to try and go beyond that very early time. But yeah, I mean, grand unified theories really try to reach that early time by trying to study the universe and particle interaction. Imagine how elementary particle physics before particles, if you wish, how string theory, for example, tries to reach that very energetic early stage of the universe.
Paul, do you have a question?
Yeah, I just heard there was a bit of excitement about the G-2 experiment, about the anomalous behavior of muons, I think.
Mm-hmm. Mm-hmm.
What is that? Do you know what that's might be showing of interest, or?
Right, so
Sorry, it's not from
no. It's a very important question that we're all asking ourselves. In fact, so there is. First, let me say what this is in kind of in broad terms, right? So the muon, remember, is this heavy cousin of the electron. I mean, it's a fermion. A fermion has the property which we call spin, which takes a certain value. And the G factor essentially describes how the muon would behave in the presence of a magnetic field. And the number that is predicted is close to 2. So that's why you would consider G-2, because then you measure a very small number. And if that number that can be predicted very precisely, and then you can measure it very precisely if there is disagreement between those two things. Remember these kind of reasoning that I was going along towards the end of my talk when I was describing theory 1 and theory 2 and the experiment. Let me go back to that slide if I can. Here, right? So imagine that you got a quantity, let's call it G, which is close to 2, so you consider G-2, and so you consider that that value. And imagine that at some point, having started from a situation where your experiment wasn't very precise and your theoretical calculations weren't very precise, you begin to see some, what we call a tension between theory and experiment. So they seem to disagree. You can see from this drawing that the black line seems to be less close to the experimental line than the red one. But you can't say anything kind of definitive because you haven't got enough precision. But now imagine, which is exactly what has happened with the G-2 experiment, that your theoretical calculations become a lot more precise, that your experimental data becomes a lot more precise, and you see a disagreement between theory and the standard model and your experiment. So you know that there is a gap, there's something that is going on which is not described by the standard model, and you need to ask yourself, what is it? So remember then when I said there could be other particles that we haven't observed yet, maybe those particles are very, very heavy. They cannot be observed directly at the Large Hadron Collider, but maybe they could be manifesting themselves as anomalies, as deviations of quantities that can be measured very precisely, which then appear not to be in agreement with the very precise prediction from the standard model. So now we have this disagreement, which seems to be really well established. The theory is solid, the experiment is solid, and so we have this very awkward tension between prediction from the standard model and experiments. And now we need to investigate what it is. And so there are also other anomalies that have been measured, for example, by one of the experiments at the Large Hadron Collider, the so-called LHCb experiment, which studies rare processes. And they also see deviations from the standard model. And so now we're trying to piece all these things together, and the theoretical colleagues are kind of developing all possible explanations. One of them is the existence of leptoquarks. I mean, the leptons and the quarks kind of do not live together in the same particle, but there are theories that predict the existence of particles that kind of combine the properties of leptons and quarks, and those could be, for example, one of the explanation. And there are lots of other possibilities. So our job now is to explore all of those possibilities, to try and first consolidate this evidence, because you want, I mean, big claims require big responsibility, right? You want other experiments to see something that kind of reinforces that anomaly, and then you want to figure out what it is. So it's a very hot question in particle physics. It's kind of a joy because it means we are living through a very exciting time where there's exciting stuff to be figured out. And the way to go about it is to A, confirm the anomaly, and B, explore possible manifestations of various theories to see which one of them it might be.
Thank you. Could I ask also, the big field, all these different, what is your, Antonella, what is your experiments that you are doing? If you can,
right, so I work on the Atlas. No, it's a very good, and thank you actually for giving me an opportunity to talk about it. So at the Large Hadron Collider, there are various experiments, various kind of intersection points of the counter circulating beams, and mine is called Atlas. It is one of the two experiments that discovered the Higgs boson. But my interest really is in searching physics beyond the standard model. And so I want to go back to this image here. For quite a long time, I've been searching for supersymmetry. I haven't found it yet, but as I said, we're scratching the surface. It might be that it's not the vanilla type, but supersymmetry is one of those very well-established theories beyond the standard model that predict the existence of heavier particles, which are some sort of mirror image of the particles that we already know. One of these particles is known as the lightest neutralino, and it has the properties that would be required to be a dark matter constituent. The dark matter you would want, if it's made of particles, you will want a particle that is electrically neutral, such that it wouldn't have interacted in our detectors through electromagnetic force. You would want it to be massive, otherwise we would have seen it already. And you want it to have weak interactions. And so my own kind of, in the past, I'd say 10 years, around a decade, let's say, I have been analyzing with my postdocs and students, that we've been analyzing Atlas data to search for manifestation of supersymmetry. And you do that by looking for specific signatures, specific kind of properties of the proton-proton collisions, and kind of there's lots of ways in which you can do that. Some of them are more straightforward than others, so we have excluded a lot of the kind of, as I said, vanilla type supersymmetric models, but there are more complex ones. And then there are also other beyond the standard model theories that I'm really interested in, that I am exploring, some of which have to do with why neutrinos, you know, these are the particles that I was listing earlier on, why do they have such a small mass? Neutrinos are very intriguing particles. In the standard model, they are considered to be exactly massless, but there is this phenomenon on which I worked many years ago when I was a PhD student. It's just called neutrino oscillation. So neutrinos of a certain kind, remember these electron neutrino, let me go back again to the slide. There's electron neutrino, where is it? Here. There's electron neutrino, mu neutrino, tau neutrino. In the standard model, these particles remain always the same, but we have observed a phenomenon whereby neutrinos of a certain kind can oscillate, transform themselves. They're produced to be of a certain kind, and they later on end up being detected as being of a different kind. And the origin for this oscillation is the fact that neutrinos have a mass which is non-zero. So this is already going beyond the standard model. It's yet another piece of the jigsaw that tells us, actually, you know, the standard model is very good. It's nearly unbreakable, but it has gaps. And so one of the things that I'm also interested in exploring is some theories that give us an explanation as to why neutrinos are so much lighter than all the particles in the standard model, even though they have a mass which is non-zero. So my dream would be to to find physics beyond the standard model, ideally with the other detector, but in general, to be honest, it's such an exciting thing. So the G-2 results and the anomalies seen by the LHCb experiment are both very, very exciting indeed.
Thank you.
You're welcome. Thank you for the question.
Thank you very much. Are there any other questions in the, put them in the chat box?
I see you. Is that you? It's got a raised hand.
Yeah, can I ask a question?
Yeah, please do.
Oh, I can't put it in the chat. I mean, I could, but
No, go ahead, Hugh. Go ahead.
yeah. Every time I come to these talks on the Large Hadron Collider, it always sort of starts with the rationalization that you're looking at the early universe and the Big Bang and the whole cosmos.
Mm-hmm.
I've got good reason to believe that the universe is not expanding. There wasn't a Big Bang. It never happened. It never happened.
Mm.
And there's no dark energy and there's no dark matter. And the explanation is actually in the macroscopic properties of the universe. It's got nothing whatever to do with particle physics. Now, as soon as you go down that line, what I find it very difficult to make any sense of what happens in the Large Hadron Collider with this kind of soup of particles. It seems that, well, the theoreticians have gone off and racked their heads, and you've done some experiments, and we sit back and just sort of lap it up. I mean, I've got a degree in physics, I specialize in theoretical and particle physics, never understood it then, don't understand it now.
Right. Okay. So you are in good company in that there are very esteemed colleagues who do not believe in dark matter. They do not believe in the expansion of the universe. There are not very many of them, but there are a few who, for example, develop kind of modified theories of gravity. I am an experimentalist, right? So, and that maybe answered also the second part of your question. I work with data. I mean, the reason why I decided to become an experimentalist, not a theoretical physicist, is that I like nature to speak to me through the measurements that we do. So yes, there are some hardliners that do not believe in the existence of dark matter, but there is quite a lot of overwhelming evidence. Maybe we are misunderstanding something very deep and very fundamental, but so far there isn't terribly strong evidence that would be the case. In terms of the theoretical physicists are having a ride and kind of taking us on a bit of a kind of excursion. Of course, there's many theories, not many of them turn out to be correct. This is why we do experiments. But for example, with the G-2, we do see cracks. We do see evidence for kind of anomalies at the Large Hadron Collider. We are analyzing that. Even if we didn't find, I would like to counteract this concept that unless we discover something new, the Large Hadron Collider isn't doing a worthwhile service to the advancement of science. First of all, we did discover something new, right? We discovered the Higgs boson. Now we have to study the properties of the Higgs boson. There is narrative that one follows. I like to search beyond the standard model of physics, and that's what I spoke about today. But ultimately, it's the data that speaks to us. And so, yeah, I hope you will maintain an interest in that. But I mean, in terms of ideology, I don't know if I can counteract that.
Thanks, Antonella. I think Paul has another question in the chat.
And you can tell I find the whole area extremely fascinating. Is then, I mean, you said at the beginning that you sort of, the Large Hadron Collider was not doing anything to do with this dark energy, the thing that.
Not right now, no, it's not. But I think that our kind of future missions might try and give answers to that. But I'm afraid I'm not completely au fait about the most recent developments. I'm certain that cosmologists are working very hard on that, but I wouldn't feel qualified to give you the latest news on that.
Okay, I don't know if there are any other hands up or questions in the chat. I mean, thank you very much, Antonella. You've been really fascinating to listen to and to see your slides. It's been a really interesting talk, I thought. And you've been talking now for quite a while, so I guess you could do with a break.
Yes,
thank you very much.
Thank
you for the invite again.
And thanks
thank
very
you
much
for
for your interesting graphics too. Very novel ones. It's like and putting it local to Leeds, your map of the collider around Leeds is very good.
Yeah.
Well, yeah. Well, thanks
Thank
very much indeed. That was great, and we got the recording, and we can make it available to those who couldn't make it tonight, and that'd be excellent.
Excellent, and thank you again also for all the questions, exciting and thought-provoking questions. So thank you for those as well. Have a good evening, everyone.
Thank you very much.
Bye.